All right, today we are going on an epic journey, not through some far-off land, but right inside the human body. We're going to follow a single dose of medicine from the second you take it to the moment it actually starts to work its magic. So, how does it do that? Let's dive in.
You know, that is a fantastic question. It almost seems like magic, doesn't it? How does that little pill travel through your whole system to zero in on your headache? Well, it's not magic. It's a whole field of science called pharmacokinetics, and it all kicks off with one absolutely critical first step: absorption.
So here's the deal. Before a drug can do anything useful, it has to get from where we put it, like say our stomach, into our bloodstream. You should really think of it as a biological obstacle course. The drug has to break free, navigate all these different barriers, and finally cross the finish line into our circulation before its mission can even begin. Okay, so every race has a starting line, right? For a drug, that's the route of administration, or just how it gets into the body. And believe me, this first choice, whether it's a pill, an IV, or a patch, is so critical. It shapes the entire journey from start to finish.
So, as you can see here, each way in has its own pros and cons. The most common route, just taking a pill, is super convenient and safe, but the absorption can be a bit slow, even unpredictable. Then you've got an IV drip. Boom, 100% of that dose goes straight into the blood, instantly. That's perfect for emergencies. And then there's something like a skin patch, which gives you this slow, steady, controlled release over a long time. Each route is a completely different strategy for a different goal.
All right, let's really dig into these two, because the difference is night and day. An IV is like teleportation. It completely bypasses the gut and gives you 100% bioavailability, meaning every last bit of the drug gets into your system. A pill, on the other hand, has to survive the brutal acidic obstacle course of the stomach. Some of it always gets lost along the way. And that is exactly why you can't just pop an insulin pill. Our gut would just chew it up and destroy it before it ever had a chance to work.
All right, so the drug is in the body. Game on. But now, it hits its first major roadblock, a barrier standing between it and the bloodstream. I like to call it the body's great wall, the cell membrane, and every single drug has to figure out a way to get across it.
So what is this wall anyway? Well, at its core, it's basically a fatty layer, a lipid bilayer that acts as a really selective gatekeeper for all of our cells. It's designed to keep most things out, only letting very specific things pass through. It's basically our cellular security system.
But here's the really cool part, the secret to the whole thing. This wall isn't an impenetrable fortress. It's not made of brick. It's more like this fluid, kind of oily sea that's constantly moving, and it's got these protein gateways just floating around in it. And this unique structure is exactly what gives drugs a chance to sneak through. They can either try to dissolve right through the oily sea itself, or they can find one of those special protein gateways to let them in.
So how in the world do they get across? Well, drugs basically have two main strategies. You can think of them as the secret back alley and the exclusive VIP entrance. Okay, so the most common way in, that's our secret passage, known as passive diffusion. It's the simplest way across, and it requires zero energy from the body. The drug just moves. It goes from an area where there's a lot of it, like your gut right after you take a pill, to an area where there's not much of it, like your bloodstream. It's just a natural flow.
And what's pushing it? It's just that there's a whole lot of drug on one side and not much on the other. Molecules just naturally spread out from a crowded space to a less crowded one until things even out. The only catch? For this secret passage to work, the drug has to be lipid-soluble or fat-loving, so it can dissolve right through that oily membrane wall.
But okay, what if the drug isn't the dissolve through the wall type? What then? Well, then it needs a VIP pass. This is our VIP tunnel, called carrier-mediated transport. Here, you have these specialized proteins sitting in the cell membrane that act like personal escorts, grabbing the drug and physically pulling it across to the other side.
And this is where things get really specialized. It's not just any protein. It's shaped to fit a particular drug, just like a lock and key. It's like a custom-made taxi service. The carrier protein binds to the drug, changes its own shape, and literally carries it across the membrane. It's an incredibly efficient way to get important molecules and certain drugs into our cells.
Okay, so here's where the two paths are totally different when it comes to speed. With passive diffusion, the secret passage, it's simple. The more drug you have, the faster it gets absorbed. But with the VIP tunnel, there's a speed limit. It's kind of like a shuttle bus, right? It can only take so many passengers at a time. Once all the protein escorts are busy, the system is saturated.
It doesn't matter how much more drug is waiting in line, you're not going any faster.
But wait a second. Just when you think you've figured it out, the body throws a curveball. It doesn't just have VIP tunnels to let things in. Some of those protein gateways are actually bouncers at the door. These things are called efflux pumps. And yeah, they are literally bouncers, whose job is to find certain molecules, including some drugs, and just kick them right back out. It's a defense mechanism that can seriously mess with how much of a drug actually gets absorbed.
Okay, so we've got our starting line, we've got the wall, and we know the secret passages. But there's one more huge factor in this whole obstacle course, the environment. Specifically, the local acidity, or pH. And this can act like a secret power-up or even a cheat code, making a drug's mission way easier.
Now, this is going to sound totally backwards, I know. You'd think that the super harsh acid in your stomach would be the enemy of any drug. But for some drugs, it's actually their greatest ally. How is that even possible?
Well, it all boils down to one simple thing: electrical charge. That oily, fatty cell membrane, it hates charged molecules and repels them. So to get past that barrier, a drug has to go into stealth mode. It needs to be uncharged or non-ionized. And here's the kicker. Whether a drug has a charge or not depends entirely on the pH of where it is at that moment.
Let's use a super common example: aspirin. Aspirin is what we call a weak acid. So when it's swimming around in the highly acidic environment of the stomach, it stays mostly in its uncharged stealth form. And in that state, it just slips through the stomach's fatty lining like it's not even there, and gets right into the bloodstream. If it had to wait until it got to the more neutral intestine, it would pick up a charge and get stuck. Pretty clever, right? So when you put it all together, the really crucial thing to remember is,
Man, we have covered a ton of ground on this crazy journey. So for a drug to actually win this obstacle course, it has to nail these three things. First, it has to pick the right starting line. Second, it has to find a way to get past that big cell membrane wall. And third, it has to use its environment, like the pH, as a secret weapon.
You know, this quote from the research really just nails it. When it says physicochemical properties, that's the stuff we talked about, like whether a drug is an acid like aspirin. The nature of the drug product is just the route, a pill, a patch, an IV. And the absorption site is the environment itself, like the stomach or intestine. It's this incredibly complex dance between all three.
and all of this, it leads to one really mind-blowing question for the future. Now that we understand this whole system of VIP tunnels and bouncers, what's next? What if we could design smarter drugs? Drugs that are basically designed like a Trojan horse, built specifically to trick the body's own transporters into giving them a free ride right past the walls. The future of medicine really might depend on mastering this epic journey. Thanks so much for joining me.